This presentation is going to look at the construction of binary adders as combinational circuits. We'll explore half adders, full adders, binary ripple carry adders, and subtractors. The arithmetic functional blocks that we'll be discussing in this presentation are typically designed to operate on binary input vectors, and they produce binary output vectors. An arithmetic circuit is a combinational circuit that performs arithmetic operations such as addition, subtraction, multiplication, and division with binary numbers, or with decimal numbers in a binary code. We'll develop arithmetic circuits by means of hierarchical and iterative design. The arithmetic blocks we're looking at often require the same subfunction to be applied to each bit position. So we can design a functional block for the subfunction and then use it repetitively for each bit position to get the overall result. The subfunction blocks are referred to as cells, and the overall implementation is an array of cells. Cells are often identical, and the overall block is called an iterative array. This diagram shows a block diagram for an iterative circuit that operates on two input vectors and produces an in-output vector. There are two lateral connections between each pair of cells in the array, one from left to right and the other from right to left. Optional connections are indicated by dashed lines and exist at the right and left-hand sides of the array. Number of connections used and their functions can affect both the cost and the speed of an iterative circuit. As we saw way back in Module 1, simple addition consists of four possible elementary operations. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is equal to 1, 0. The first three operations produce a sum requiring a 1-bit representation, but when both augend and addend are equal to 1, the binary sum results in 2 bits. Because of this case, we represent the result by 2 bits, the carry and the sum. A combinational circuit that performs the addition of 2 bits is called a half adder. One that performs the addition of 3 bits, 2 significant bits in a previous carry, is called a full adder. Let's start by taking a look at the half adder. This is the truth table for the half adder. The input variables are the 2 bits to be added, and the outputs are the sum and the carry. We can obtain equations for these fairly easily, since the carry is only 1 when x and y are both true, and the sum is an exclusive OR. From here, it's pretty easy to implement the half adder, assuming that we have an exclusive OR gate available to us. There are alternative implementations available depending on the underlying technology netlist. Now, let's take a look at the full adder. A full adder is a combinational circuit that forms the arithmetic sum of 3 input bits. Besides the 3 inputs, it has 2 outputs. 2 of the input variables denoted by x and y represent the 2 significant bits to be added, and the third input, z, represents the carry from the previous lower significant position. Here we see the sum of products form of the 2 outputs for the full adder. And we can actually simplify those outputs a little bit further by using k-maps and even get a bit more clever if we have an exclusive OR made available to us. Here we see the logic diagram for the full adder. Now let's take a look at the binary ripple carry adder. A parallel binary adder is a digital circuit that produces the arithmetic sum of 2 binary numbers using only combinational logic. The parallel adder uses in-full adders in parallel, with all input bits applied simultaneously to produce the sum. Here we see an abstract implementation of the circuit. The full adders are connected in a cascade, with the carry output from one full adder connected to the carry input for the next full adder. The carry from each is connected to the input for the next. A 1 carry bit can obviously extend throughout the circuit, so that's why we call it a ripple adder. The 4-bit adder is a typical example of a digital component that can be used as a building block. It can be used in a lot of different applications involving arithmetic operations. The design of the circuit by the usual method would require us to make a truth table with 512 entries, but by cascading the 4 instances of a full adder, it's possible to obtain a simple implementation without directly solving the larger problem. In this case, subtraction has helped us tremendously. Binary subtraction is a bit trickier. As we saw in section 1.3 of the text, we do subtraction by comparing the subtrahend with the minuend and subtracting the smaller from the larger. The use of a method containing the comparison operation, however, results in inefficient and costly circuitry, so we need to look for another way to do this. As an easier solution, we can simply subtract the subtrahend from the minuend. If no borrow occurs in the most significant position, then we know the subtrahend is not larger than the minuend, and the result is positive and correct. If a borrow does occur in that most significant position, as indicated in blue here in this example, then we know that the subtrahend is larger than the minuend. The result must then be negative, so we need to correct this. The image on this slide shows the subtraction algorithm. Subtraction of a binary number from 2 to the n to obtain an n-digit result is called taking the 2's complement of the number. So in step 3, we're taking the 2's complement of the difference. Here, we can see the algorithm at work. We have an n bar of 1, which necessitates a correction of subtracting the initial result from 2 raised to the 8th to get the final result, which turns out to be negative. To do subtraction with this algorithm, we require a subtractor, an adder, and possibly a 2's complementer to perform both addition and subtraction. Here we can see the block diagram for a 4-bit adder subtractor using functional blocks. Now this circuit is a bit more complex than necessary, so to reduce the amount of hardware, we can share logic between the adder and the subtractor using the notion of a complement. There are 2 types of complements for each base R system: the radix complement, which we saw earlier for base 2, and the diminished radix complement. In base 2, 2's complement is the radix complement, and 1's complement is the diminished radix complement. Given a number n in binary format having n digits, the 1's complement of n is defined as 2 raised to the n minus 1 minus n. Alternatively, you can just flip the 1's and the 0's, or exclusive OR the number with the string of all 1's. You can also think of it as subtracting 1 from each digit, so there are multiple ways to go about getting 1's complement. 2's complement can be obtained by adding 1 to 1's complement. Also, 2's complement can be formed by leaving all least significant zeros and the first 1 unchanged, and then replacing 1's with zeros and zeros with 1's, and all other higher significant bits. After we have 2's complement, we can perform subtraction using it. We can simplify the hardware by sharing adder and subtractor logic. And armed with the complements, we're prepared to define a binary subtraction procedure that uses addition and the corresponding complement logic, as shown here in this algorithm. Thank you so much for watching. Be sure to work through the examples with your textbook and to check La Lima for updates.